Hey, good morning, everybody. Welcome to the NANOG 76 Hackathon. So I'm Michael. I'm going to give a really brief introduction of what's going to be happening today, and then I'm going to pass it over to Syed and Deepak from our sponsor, Oracle, who helped put this hackathon together, along with Hussein from Tesuto, who helped provide all the virtual lab infrastructure that you'll be working on today. So after I'm done talking and Syed is done talking, we're going to encourage everybody to form teams to then compete on this. I know that there's been a lot of great activity in the Slack channel where people were coming up with some ideas to work on. Saeed and Deepak are also going to go over some exercises that you could choose to complete instead. So if you decide to go that route, please form a team of about 5, and it looks like people have grouped off already. Otherwise, if anybody, once the introductions are done and the presentation is given, if people still have had a problem forming a team, please either come up and talk to this table here that has Hussein, Jeff, and Steve from the hackathon committee. So we'll be able to help you out, either form teams or help out during the hack. And then also our friends from Oracle, please wave, Oracle table. You could thank them for sponsoring this, as well as go to them and ask for help on whatever it is that you're working on. I just want to also give you a little overview of what's going to happen during the day. So we're going to give this introduction. Afterwards, you're going to form teams and start working. We'll break for lunch at around noon. We'll break again during the middle of the day and keep you well fed and well hydrated as you work. We're then going to have presentations where everybody here gets to present your work at 6 o'clock. You'll then vote for who you think is the best team. Then we'll break and have a little reception outside. So any questions, please come and talk to me or one of the other friendly people who raised their hands just a moment ago. And then I'd like to pass everything over to these two who will go over what you're going to be working on today.
You guys can hear me? Okay, cool. My name is Syed. I'm a network engineer in Oracle Cloud Infrastructure, and I'll be presenting with Deepak. And I also have, like Mike pointed out, a bunch of other team members who will be helping me out throughout the day, running the hackathon and answer any questions that you might have. So let's get started. So let's say if we have a network topology that look like this, just a couple of endpoints with a few switches in between. And if there's a failure in the network, it's relatively easy to identify a failure in a simple network. And once we have identified the failure, we can fix it, and everything is in healthy state, and we're good to go. But the reality is, we have network that look like this. So with a core distribution and access layer, and you might name those layers differently, but there is redundancy on each layer. Or even if we are using class fabric, it's a really densely connected topology of a spine of leaf nodes. It's really complicated network. Or if we look into the data center, it might look like this. But we're not here to solve structured cabling problems. We're here to talk about network monitoring, and that's the theme of our hackathon today. So we'll be talking about active monitoring. So just give you a quick overview of agenda today. I'll go over the problem statement, then we'll talk about the hackathon goals. If you're a task that each team needs to complete for the hackathon, I'll give you a brief overview about the topology, and then we will talk about different tools and protocols that we think might help you solve the problem. But feel free to use any tools and protocols that you think is more reasonable to solve the problem. This is just to provide you a guideline because we have varying set of skills in the group. So just to get you started, give you some base to work on. Okay. So just the code, the opposite of networking is not working, said someone smart, and I kind of agree to that. So what's the problem that we are trying to solve today? So in a large-scale, dense, complicated network, we need tools that can identify and isolate failures so we can fix them, and we have more robust network that's highly available. And network active monitoring is a great tool to use because it uses sensors and agents to simulate customer traffic, and it can test for end-to-end reachability. It can test for packet loss, and can test for latency across the network. But the thing is, since if you have used active monitoring, it uses probes, and if you have multiple active paths in the network, how you can make sure that your probes are covering all the active paths in the network. And I explain more on that in the next slide. Yeah. So on the right, we have the topology that we'll be using in the hackathon today. So you have 6 routers and 2 hosts. Considering all links have equal cost, between host A and host B, we have 4 possible best paths that we can use. R1, R2, R4, R6, R1, R2, R5, R6, R1, R3, R5, R6, or R1, R3, R4, R6. So how we can make sure that when we are sending a probe, it covers all those 4 possible paths, because normally if I'm just sending a probe from host A to host B, it'll go to R1 and it can either go to R2 or R3, and from R2 it can either go to R4 and R5. And I know I'm skipping some of the Icmp hashing details, but this is just to keep it simple. Let's say we have all equal cost paths, and we're just talking about if a probe is going from host A to host B. So how can we come up with a mechanism that we can more deterministically tell that a probe will take a path A, or and then a second set of probe will take path B, and then in that way we can cover all 4 possible paths and identify any failures as it happens on any of those 4 paths. So that's the goal we will be working towards. And just the stepwise, what are the hackathon goals? First one is we expect every team to extract the topology information using some kind of automation. Then once you have the topology information, you can build a graph or network map using node links and matrix. Once you have the graph, you can use that to compute all the best possible paths between 2 endpoints. In our case, it will be host A and host B, or dev1 and dev2 boxes. Once you have all the best paths calculated, then you can construct a probe packet and make sure that you can probe all the 4 possible best paths in the network. Then once you have that, you're probing all the best paths, just introduce a failure in one of the paths and make sure you can account that using your probes. And there's a bonus one if you can visualize the collected data in matrix. So that'll be the bonus part. Okay. Just a quick overview of topology. Again, on the right, you can see the topology diagram we'll be using today for the hackathon. I have included all the interface and IP information, so it's just a quick one-stop shop to look at all the details in the network. We have 6 Juniper VMX instances, R1 through R6. We have 2 Ubuntu hosts, dev1 and dev2, connected to R1 and R6. We are using ISIS as the IGP, but feel free to change it if you want to. We have configured BGP-LS on R1 and R6, and on dev1 and dev2, you can run a ExaBGP instance to pair with R1 and R6, and we'll talk more about BGP-LS next. So any questions so far before I start talking about protocols and tools? Yeah, so in the end, we'll have the links for all the necessary documents that you'll need. Okay, cool. So BGP-LS. What is BGP-LS? BGP-LS is basically another NLRI of BGP, defined in RFC 7752. What it does, it uses BGP TLV fields to define objects. So that's like nodes, links, and IP prefixes. And then it uses a new type of BGP path attribute to define attribute. It's a non-transitive optional attribute to define attributes of all these objects. So like node attribute can define node name, router ID, multiple topology identifier. Link attribute can define local IP, remote IP, local and remote router ID, and the bandwidth available on that particular link. So what can we use it for? So let's say if I have a topology and I'm trying to build a topology map for it and to use for like offline path computation or TE purposes, and my network has multiple IGP domain. So I don't really need to have a host in each IGP domain to collect node information from that domain. I can just export my IGP into BGP-LS database and then just use BGP-LS to communicate to the rest of the network or any external entity to distribute all the node and link information in my network. If you still feel like what the heck I'm talking about, so hopefully this will give you a bit more visual details to it. So this is basically a snippet from Juniper Router showing you 3 nodes. And if I look more into, the first one, you can see it has information about router ID, host name, what protocol it's running, what area it's part of, and all that good bits. And if I look into BGP-LS for the link, you can see it has information about local and remote IP on that link, what's the local and remote router ID, what's the TE metric for that link. So once you have that information, you can pretty much define the topology using it. And like I said, you can run ExaBGP with R1 or R6 to get that BGP-LS updates on the host, so you can process it. So here's a quick snippet of ExaBGP conf file. So the important bit is the family address I'm using, so it's BGP-LS. You can use a script to parse the JSON, the updates you're receiving from BGP-LS as JSON. You can use any script to parse that information. And this is just the message format you're going to be receiving from router to the host. The important part is, again, the NS-LS NLRI type. If it's a type 1, that means it's a node LS. If it's a type 2, means it's a link LS. If it's a type 3, means it's an IPv4 prefix. If it's a type 4, means it's an IPv6 prefix. So again, you have option that you dump these update messages to a file and then write a script in your own preferred programming language to parse the information you need to build topology, or we'll give you an overview of JQ, how you can use JQ to parse JSON and extract information that you want. Okay, so now you have information about nodes and links in a topology. You need to build a graph to be able to compute all possible best paths in the network. So there are multiple graphing utilities you can use. In Python, you have NetworkX or iGraph. In Golang, you have GoRaph. I just feel NetworkX is like really easy to use, really easy to understand. So on the right, if you see a network topology that has 3 routers in it, in Python, you can just import NetworkX library, initialize an undirected graph, and you can add R1, R2, R3 nodes, and then you can add edges. Edges is basically the links between them. So R1, R2, R1, R3, and R2, R3. And then that will give you a graph, and you can see that it has a graph with 3 nodes and 3 edges. So once you have the graph, you can run shortest path algorithm on that to figure out all the best paths between 2 endpoints. Okay, so far we have topology information, and we have created a graph to extract all the best possible paths in the network. Now our challenge begins to how we can probe all those best paths. So like I said initially, that if we are sending probe from host A to host B, it can take any path. So how we can deterministically tell it can take a path A or path B. So here, I'll just give you a quick overview of GRE. So what GRE is generic routing encapsulation protocol. What it does, it just encaps your IP packet in an outer IP header that has a new source. It can have a new source and destination. And once you de-encapsulate that outer header, it gets routed based on whatever the inner IP header is. And we are talking about here the stateless GRE. We are not talking about establishing a tunnel or anything of that sort. And in the next slide, I'll give you a more detailed example of it. So if you're interested in using this solution, I'll tell you more about it. Okay, so again, on the right, we have the topology we'll be using for the lab. So if you look at it, we have dev1, R1, R2. So if I'm trying to probe, making sure that my probe actually follow dev1 to R1 to R2, there's an illustration of header that I can use, or GRE encap that I can use to make sure that my packet take actually that path. So if you look, the innermost header, it has source and dest as dev1 IP. And if you look at the R1, or the outer IP header, it has source still as dev1 box, but the destination is set to the directly connected interface on R2 and R1. So 10.1.1.1, basically the IP right here. And if I look at the outermost header, it has the source as still the dev box, and the destination is set to directly connected interface on R1 with dev box. So what's going to happen if I send this packet through this network? So the packet will get routed based on the outermost header. So it will go from dev1 to R1. And if I have GRE decap filter configured on ingress interface, it will get rid of the outermost header. And I've included a quick snippet for GRE decap filter. It's already configured on all of the routers if you want to go use that. So what will happen, it will get rid of outermost header. So now you have a packet with source 20.0.0.2 and destination as 10.1.1.1. Since it's a destination is directly connected interface of R1 to R2, it will make sure it goes from R1 to R2. And then when it reaches to R2, the second outermost header will get decapped. So now there's a packet that has source as 20.0.0.2 and destination as 20.0.0.2 as well. So it gets routed back to dev1 box. Any questions so far? Hopefully everybody is still awake. Okay, so next we'll talk about Icmp. That will walk you over how we can construct the packets and send it through the network. And Deepak will take over from here. So just click down, click up. Oh, yeah.
So we need a tool to create the packets. And the option for you is to write your own in any programming language of your choice, Go, C, whatever, but it will take you an enormous amount of time. So something we are suggesting, but feel free to use whatever you like, is Icmp. So Icmp is written in Python. It's free. It's GPL version 2, very powerful packet manipulation tool or a library written in Python. You can write your own script with Icmp, importing the proper libraries, or you can just use it as a shell. You can open up multiple shells, one shell to send the packets, the other shell to sniff or receive the packets, and do the processing of the packets as soon as you receive it. So it can send packets, sniff, dissect, forge. You can write numerous network tools just with Icmp. And those tools, discovery, scanning, trace routing, some of the buckets for those kind of tools. So let's get into Icmp. So I'm having a simple example, which is just creating an IP packet with Icmp. So I've opened up two shells, and the center you see Icmp, by the way, you have to run Icmp as root or sudo. You cannot run at your user level. So all your pods have Icmp. You can open up two shells when you start playing with it. This is just for Icmp echo request and reply. The bottom screen of the screen, you see the shell which is sniffing. You're showing the interface, you're showing the filter. You have to use a proper filter to tell what source or destination IP you're expecting, what type of packet, it's Icmp or TCP or whatever, and how many packets if you want to just receive few packets. You can run it indefinitely. You can specify the number of packets, or you can run in a for loop. You can do numerous things with it. Once you receive a packet, you can do a summary of it, and it will tell you what packet you received from where and what timestamp is, which is one important thing when you're probing, is you want to see the round trip time. So on the top, create an IP packet, show the source, destination, ICMP, that ICMP type, put a payload if you want to, and then construct the packet by putting a slash between all the different constituents, and then use the send of SCAPI to send that packet over the wire. And the other side, you are sniffing it, and you are getting the packet on it. SCAPI is powerful enough. If you have a GUI, then you can even see the diagram of like what the packet looks like when you send it and when you receive it. So you can see the different constituents of the packet. And here I'm showing that this is the source destination on the left side, what you constructed, and what type of request it was sent, what was the payload, and on the other side, the received packet from this particular thing. So if you want to run it in a for loop, it's simple, just use Python. Range 5, put 5 packets, same payload, send packets. The receiving filter changed because now we have 5 as a count, and then we are specifying a Lambda function which is doing a summary on each one of them. So you can write your own separate function where you can specify what you want to do with the packet, right? The received packet. You want to get the timestamp, you want to get what was the payload of the packet, what was the source address, what was the destination address. So going back to what Syed was showing up in the IPGRE like sequence of packets which you are creating, you can play with the payload and put in stuff in there, some sequence number, some timestamp, something, and then when you receive the packet back, open it up and see what is in the payload, and then compare it with the time you received it. So just giving you an idea of like how SCAPI can be useful. Any questions on SCAPI? Now, let's move on to JQ. So Syed was pointing to the output from BGPLS, which is a JSON. We need something to parse that JSON, because for probing or finding the different paths, you will have to process this JSON and get the links and nodes out of the output. How do you do that? You can write your own Python program, you can write in Java, whatever programming language. This is just a suggestion on one of the tools which you can use, but feel free to use whatever you want to use, right? So JQ is a very lightweight JSON processor. And you know, like most of the vendors now allow you to convert your CLI output into JSON. And also like ExaBGP or any other tool. By the way, we have ExaBGP already installed on the part. So if you want to use it for BGPLS and the output which you'll get from the parser, you can take that JSON and run it through JQ to find out all your links and nodes. So what is JQ? It's same as like in the same family of tools as like SADOG, grep. And if you look at for YAML, there is YQ. For XML, there is XML Starlet. For HTML, there is PUP, which is in the same category of tools, single tool with no dependencies, which you can install written in C, and very, very powerful. And some extra stuff on JQ, it's in the domain of the functional programming languages. So you have things like map, filter, select. You can do flat map and other things. It's Turing complete. So you can take JQ and you can run, or you can write an interpreter for, someone has done it actually, an interpreter for a programming language called brain followed by a curse word starts with F. And that programming language, they have written an interpreter in JQ, which is Turing complete. And what it means is anything which is computationally feasible to solve can be solved with JQ. So that particular language is just 8 set of commands and instructions. And it's Turing complete, and an interpreter for that particular language is written in JQ. So what I'm trying to say, it's very, very powerful. It's a full feature set of a programming language like Java, C, or any other language which you normally use, which you can do it in JQ. So for going through JQ, what we did is like just a simple example. This is the CLI output on the left, and you have a JSON output on the right. You pipe it through this JSON, and you can get the JSON from this Juniper router. So there are two blocks of it, two interfaces. The first block, I have shown an equivalent JSON which you'll receive from the conversion of this into JSON format. The first and foremost important thing this is to understand the schema. You can use whatever you want to use. There are a number of tools online. You can cut and paste the JSON output there, and it can tell you the schema of the JSON. Or you can go and read through this JSON and try to figure out what are the different attributes in the JSON, what are the different arrays in there, how many nestings of arrays in there, and how can go to a particular level, and then filter it out. The NLRI types is something what you might have to look for to find out the links and nodes and go through your JSON, and JQ can help into that. So we'll just concentrate on the first block because I didn't want to put too much on in terms of JSON, formatted JSON on the screen. So the top one is the interface, what the interface is, what the ISI's agency level is, what the state of it, priority, IP address, and other things. So I mean, if you guys are used to VS Code, you can just use a plugin like JSON to TS and then quickly get the schema of your JSON. And you will see there is, at the top level, there's a root object which contains an array of ISI's adjacency information. Then ISI's adjacency information contains attributes and ISI's adjacency, another nested array into it. And that nested array, ISI's adjacency array, has all the details which you need about the like if you want to figure out what the interface is, what the name of the interface is, and if ultimately if you want to create a CSV out of it. So the basic filter is a dot. JQ has a concept of filter. If you say JQ single quotes dot and use it with your XML, with your JSON, you can get a pretty print of your JSON. That's a pretty print filter. The first one after that, after the dot, is two square brackets. The square brackets opening and closing, which is like a flat map of a functional programming language. So it takes out the outer, what you call the one after the ISI's agency information. That's an array, the top array. It will take it out. It's like a flat map and gets you into the contents after that. So let's say if you were interested in the XML NS attribute of it, that's how you will write you've taken out from the outer array, then you've gone into the first element of it, and because there is only one element inside that outer array, and then you go into the attributes, and then you want to get the XML and NS value of it. There is an online tool called jqplay.org if you don't want to do it on the command line. As you try out playing with JQ, you will see the output on the right, and then you can construct this. You would not do it in the production environment, put your all the JSON on a website like jqplay.org, but for this hack, at least you can try it out and construct and play with this thing. So if you want to go into the ISI's adjacency, the zero, and the adjacency details, you have two blocks. The first one you want to go into the first interface, and you want to get the name of that particular interface. So this is the JQ query. You can either pipe it, because it works like streams as well. So you can get the JSON file and then pipe it to JQ, and JQ would print the name of the interface with this particular query. Then if there are multiple elements in an internal array and you want to filter it out with a particular criteria, here I'm trying to filter it out with a select. Select interface name, the data, which the data constituent is AE 0.0. So it will go into and just get the AE 0.0 element of that array, internal array. Then the goal is to create a CSV. So there are different operators in JQ. You can form a JSON object out of the intermediate output obtained from JQ. So the last part of this JQ query, if you see after the select, the last pipe is creating a custom JSON system name and interface name, which you see in the output. You can give any name of the property we want to. But that's what you are getting it, which will be used for creating a CSV. So in this, what we added is square brackets, system name and interface name, and then we are passing it to @CSV, which spits out the CSV output. This is just for one element of the array in that particular table. So I mean, it's too much to grasp in this 10 minutes, but you have this PowerPoint, you can look through it and go through the example and see it. One additional thing is raw output in this JQ statement. This raw output is to making sure that you proper, like JQ will try to escape the double quotes, which is there in the output, like VMX 1911, that is in double quotes already. The data is already in double quotes, so it will try to escape it out. You don't want those extra double quotes, so you can just use a raw output. On jqplay.org also, you have a switch to turn on the raw output or a compact output, or there are different options online. This one, little bit change in the select query, but now you are able to glean all the interfaces from the table. And that's the CSV. So think all links, all nodes in this format. Any questions on JQ? You can write your Python program to parse the JSON, any language of your choice. No, for JSON, there's nothing better than JQ. If you want to, if you're thinking in terms of SADOC to do things rather than writing a full-fledged Python program to parse your JSON. Key thing, understanding the schema, that's one. If you understand the schema, this particular tool allows you to quickly frame queries. Okay. So now the bonus part, if you want to do visualization, Grafana is already installed. InfluxDB is already installed. Grafana is running on the normal port 3000. You can format your output from what you get from JQ into, or what you want the probes to look like. Syed suggested some R1, R2, R3, R5. You can create those probes and kind of like you create those probes, and then you run your program with Scapy to send to the different devices. Once you get the packet back, you open it up, you check what you got in that, try to create kind of like something which you can insert a time series data into Influx. Once it gets inserted into Influx, you can see it on Grafana. So this one example, this is the format. It's called line protocol format on Influx. You can create a text file like this. You can import into Influx. I'm using two tags, the probe number and the time, the RTT time and the sequence number. If you are using something like a sequence number or the probe number, it's up to you to design whatever you want to do. And then the timestamp at which you receive the packet back. These are the data points for Influx. You can import Influx into import this data into Influx with this. Once you are on Grafana, admin is the password. On your part, go to port 3000, log in, and then you have to configure for the first time. It will ask you to change the password. You leave it as the same as admin, and then you show the data source as Influx. Try to connect it. Influx by default runs on port 8086, and then you can check the connectivity, and you should get something. The data source is working properly. So and then you have Grafana, you have panels, and you can create the panels. You can specify the query, like what probe, what value you have to look for. You can create multiple panels. So play with it. If you reach to the bonus stage, if you need help, we are here. We can point to like write tutorials or whatever. There is already some links there, or we can help you to create the dashboards. So these are the packages already installed on the part: Scapy, NetworkX, XRVGP, JQ, Influx, and this is the credentials and the login details. Questions for both of us? Good. You take this.
So again, special.
It's on.
Okay. So again, special. Is it on now?
Yeah.
So special thanks to Tesuto for setting up lab for us, and you'll see a paper with all the details, how you can access the lab. And from here on, let's get started. These are all the links, probably. You'll need to, so like Scapy cheat sheet, JQ playground that Deepak mentioned. Oh, you cannot hear you? Okay, cool, better. Okay, so all the useful links. So Scapy cheat sheet that you can use to construct packet, JQ playground that Deepak mentioned, some Grafana docs, and Git repo for getting all the slides and actually some of the documents. So there's a nice diagram of topology that you can pull from if you just clone that Git repo on your laptop. So you'll get all the slides and other information that we have put in that Git repo. I'll leave this slide on so you can use all the links on this slide. And let's get started. I'll give it to Michael.
Thanks. So does anybody not have a team? Okay, we have just one person. Okay, so anybody who doesn't have a team, please raise your hand. So everybody, look around at so the people that have raised their hands, you could go and talk to other people to see what they're working on. And anybody who does have a team and saw somebody raising their hand, if they want to be kind enough to reach out, maybe say like, hey, you should come and join my team because my team's going to do this amazing thing. So once your teams are formed,
we're going to give people an opportunity to present their project ideas and attract team members?
yeah, would anybody like to, so anybody who is not working on the goals that Syed and Deepak presented on, if anybody's doing their own project, would you like to come up here and pitch to the 3 people who do not have teams? Oh, thanks so much.
Hi, I'm Ryan Rodden. I'm a network architect with Conversant, based out of Chicago. And I'm going to be continuing, hopefully, a project that started at the first NANOG Hackathon in 2016, which was to assemble commodity console servers from Raspberry Pis or similar hardware. The goal was to have it be kind of self-discovering, SSHing back to the central server so that you can SSH directly into the device across firewalls and other network boundaries. I have them be self-discovering, so you have a single view of all consoles and their downstream connected devices, ideally a WebSockets browser client, so you can point and click to gain access to the downstream devices through the browser, and a bunch of other use cases that would help, rather than having to talk to somebody in a remote office through connect, to this console port and WebEx here and type these commands to get, fix something or deploy a new network. This is a device you maybe could ship out with a 4G dongle attached to it, and it phones home as soon as it's powered up and plugged into something. It can also be used within data center networks and other locations. So in NANOG 67 Hackathon, we had developed a framework where it's self-registered with the main API. You could see the list of active devices and their downstream ports that were available. They open the SSH connection back to the specified SSH server. And the next steps would be working on getting that console port exposed via a command line or SSH access, and then ideally the WebSocket server and client, if anybody is interested in that. This is all in Python 3, so anybody who's comfortable with that and knows WebSockets in particular, I have no knowledge of that and could use help with that aspect of it. So if anybody's interested, I'm over there. I've got some hardware with me to help facilitate development and testing as well. Thank you.
Thanks, Brian. Anybody else? Okay, so once you have your teams formed, please send a representative up to the front table to get some instructions on how to set up your virtual infrastructure, as well as let's know what pod you are so that everybody's not going to try to work on the same virtual infrastructure, and then you can also write down all the members of your team so we know who's working on what project. Okay? Any other general questions? All right, good luck today. If you have any questions, you could visit this table up in the front or the table way in the back, and one of your friendly hackathon mentors will help out. All right, bye.
Okay, so we followed the guide today, and basically an overview of what we did was we established BGP in the dev boxes, received and parsed link state information with X of BGP. We fed that into Network X to build a graph and adds weights and edges so we can calculate the best path using Network X. And then finally, we crafted some packets with Scapy to test link failure scenarios. So first, basically, we ran into an issue with X of BGP at the beginning. We didn't think it was installed just because the binary wasn't accessible. So we lost a little bit of time doing an apt-get install, and then the Ubuntu version actually ended up having a bug where it tried to send MD5 for everything. So lost a little bit of time on that, but once we used the installed version provided, we were able to establish BGP on the boxes and then parse out. You're able to parse output via a script received for each route received. We weren't able to get that working. We were playing around with it a little bit, but we weren't able to get that JSON. So what we did as a workaround was once we had BGP established, of course, not only is the dev box receiving the route, but the Juniper is also sending the route. So we logged on to the Juniper box and just did the show route advertising protocol BGP, piped it to display JSON, copied that into a file, and then pasted it into Python interpreter, played around a little bit with that in Network X. For Network X, we just did a couple imports. We added the correct weights that were fed to us from the BGP LS information, and then using Network X, we were able to calculate best paths using the provided single source Dijkstra path method available in Network X. And for Scapy, I'm going to pass it off.
So for the Scapy, initially it got a bit tricky in at least sending out the Icmp ping packets as well, but eventually we were successful enough to at least send that, and then we started forming more packets, the GRE and CAP packets, and then sending them forward. So based on whatever information we received from the Network X, we had those many paths in there and those many packets for each of those paths, and we send them in a loop. And after that, so when we run the sniff script where we are actually sniffing for those packets, so we get for all the paths, we get these. So it calculates the RTT, and then as you see the second last field, it's like 12531 is nothing but the router path that it takes, basically R1, R2, R5, and so on for all of those paths. So we had that, and it ran successfully for n number of packets being generated. And then we did the failure scenario where we say, for instance, a link goes down between R2 and R4, and it was able to sniff and probe correctly that information, that all the routes, all the paths that included that link were down, but it was successfully able to probe the rest of the links which were still up, not using that link. So that was pretty much with the Scapy, and I'm going to give it.
Yeah, so this is what we had today. So then for future work, we were looking to actually take the data you saw on the last slide and actually record it into Influx and maybe visualize it with the Grafana. And then we can actually set up some alerts with the Grafana, let's say on link down or something like that. So that's what we have. Thanks so much for listening.
everyone. We were continuing work on the PyCon project I was describing earlier from the NANOG Hackathon of 2016. Recap of the use cases we were looking to solve were cases where you're deploying new equipment in the field or having to talk users through troubleshooting over the phone that they may not be equipped to do. The goal was to take some commodity hardware and solve this faster and cheaper than some off-the-shelf proprietary platforms that you might have a longer lead time to get and configure and deploy in your environment. The overall mechanism that was already in place prior to today is that the devices can be deployed. They call back to the central API that the agent is started with, and they report their addresses, the ports that the console ports they have available, and then they can also be given information to tunnel back to an SSH server for remote SSH access in the future. I think we're all familiar with the kind of ubiquity of Raspberry Pi and the related hardware the last few years. It's cheap, it's reliable, it's easy to stock and deploy and automate against with your software of choice. Our next steps that we outlined a few years ago, that the project's been pretty much dormant since then, was to apply some, add some WebSockets to get a browser-based experience to access the console and potentially have simultaneous use or maybe exclusivity, and then also have more UI and API enhancements so that you can interact with the data manually or programmatically to automate against it as well. So today we were picking up where we left off, and the agent does start up, it registers, it reports everything, and it gets some config information back for the tunnel server. This is nothing particularly new. In the UI, we made some enhancements for how the data is presented and also started adding the capability for the server to take some configuration data of how the console is connected to downstream devices. So in this case, the main thing demonstrated is the port descriptions, which are configurable in the device details page. You're able to click on those and edit them through the page as opposed to have to hard code it in the database or any YAML files. This came with some changes to how the console port information is aged and tracked in the database as well, so that this information and other information can be persisted as configuration. Oliver also made a lot of progress on researching the WebSockets functionality, and we got a proof of concept embedded so that multiple users can load the WebSockets. You're able to see actions replicate from one user to another. However, we don't have it interacting with the console backend yet. We do have a script made by another teammate that is able to open the serial console, and that can be embedded in the agent as part of our the next steps on the project to hopefully get some data flowing across it. So we gained a bunch of experience with researching into WebSockets and then the asynchronous workflows that come with that. I think none of us have really ever touched anything like this before. Interacting with the TTY through the Python serial module was a first for all of us as well. And then also we kind of brushed off some of our experience with Bootstrap and jQuery to make some of these UI changes and implement a few more API routes. And then I described some of those UI tweaks and progress made there. Takeaways are Flask and Bootstrap do simplify non-developer, aka network engineer and other people hacking on this. The progress is accelerated. However, when you go to do something like WebSockets and asynchronous I/O and everything else, especially through a stack like we were trying to aim for, it is much more humbling of an experience. So trying to implement the whole workflow through the WebSockets front end, the API and kind of database middle layer, and then the real-time interaction with the consoles will take quite a bit more planning, but we have a few more building blocks and proof of concepts to work with. That's pretty much it. Thanks to everybody on the team for your help today.
So hi everyone. So we are the rookies. I'm Tomena, if you want to. Pranav, Ruben, and Sadanshu, if I'm correct. Yeah. So could you go to the next slide? Yeah. So this is the roadmap that we decided to follow. We decided first to get, of course, the topology of the network, and then we tried to build the network graph. And to use this graph to get all the possible path to the two hosts. And then we tried to construct probe packets, and the last step was introducing and accounting failures but we wasn't able to do that. So we divided the team into 2 smaller groups. The first team or the first group was supposed to do the 3 first parts, and the second team was working on the 3 last parts that you can see on the board. So Pranav will talk about this overview.
So this is the overview block diagram of what we were trying to do. The ones in dark green is ones which were successfully able to do it, most of it, and the light green one were we ran out of time, we were unable to implement it. So as you can see, we use XRBGP to collect the flows, and we wrote a script to parse that information and write it to a database. For this hackathon, we just used CSV. We didn't have enough time to move it to into InfluxDB, so we just stuck to CSV. And we had visualization on one side, and we set up an alerts where US email client, if it sees any changes, it just sends us an email. And we have pro packets, which the team 2 has worked on. They'll talk more about it and integrate into the part selection. For passing the data, we took the data which was being written into a text file, and we were passing that information and writing into a CSV file, collecting all the information which we needed into 2 separate files, one for nodes and one for links, so that we have clear understanding of what's happening where. And then we used Network X to visualize this information and visualize the attributes related to that.
Hello. For the second part, we started trying to, or we were struggling to how to identify the best possible path. So we basically get the nodes and the links information from BGP link state, but at some point we assume that we are going to have equal cost, and we discard the possibility to calculate the best path from the host point of view. So we basically leave for later on. And please change. So we basically put the effort, because it took us some time to build a probe and send and automate the continuous probe sending that we basically implemented as a cron job in the device. So we are constantly monitoring the reachability.
So for future roadmap, we want to clean up instead of using CSV, use InfluxDB, and clean up the email client, have a very basic email client, and make it as close to real time as possible, both visualization as well as alerts when it comes to alerting. And best part calculation, we want to implement that, and identifying failure links and writing remediation scripts if there's a failure to go back and fix it via config change or just by alerting. Thank you.
Okay, so we're Team Pod 3. So what we did was first get a better understanding of XBGP. And what we did was once we started that process, Jeff, one of our team members, started to work on Python to parse that data. Then once we have that parsed data, then we feed it into Network X to have a network graph constantly updated as we get new information. And then Scapy was a pain. We'll talk about it really quickly. So we split it out into 2 parts. So an announce means that the path is valid. So what we did was we give Network X this data set here where it tells you, okay, router 1 has reachability to router 2, router 2 has reachability to router 1, so on and so forth. So the announce is good. The network graph will map that. If a link goes down, we send a withdrawal, and then our team member took that and took it out of the network graph. So I'm not going to linger on this. It doesn't make a lot of sense, but this is what we tried to visualize of what was going on. This was the data that was gathered from XBGP through Python, parsing it to give us this data that we fed into Network X. And then this is Scapy here. So what we did was very similar to one of the teams. We set it on these 4 paths, right? These are the 4 best possible paths in terms of hops. The ending values there show the route that it took, right? Router 1 to 2 to 4 to 6, and then 5 to 6, and so on. And that's it. So, oh yeah, future roadmap. We'll get Influx working with Grafana. Thank you.
So, hi everyone, we are Team NetBuffs, and we are students in the University of Colorado Boulder. So, honestly, this hackathon was a little overwhelming for all of us because of the number of tools and the number of objectives we had to achieve. But yeah, I think we tried to manage and try to do what best we could do in the given amount of time. So this is the topology that we were given, and from that, we tried to find out all the best possible paths using NetworkX tool. And we could find out these number of paths based on which we tried to build network monitoring logic. So this is a code snapshot. This may not be visible to all of you, but what we have done here is we've used KP to, based on the number of paths that we found using NetworkX, we use KP to create those number of pro packets for the number of hops based out of each of the route that we got. And those pro packets will be sent from dev1 to dev2, and a response will be received from dev2. So the pro packet that we created, each of those pro packets had the timestamp value for the time the packet was sent at, and when the packet is received with the timestamp of the arrival time. So we took out the time difference to find out latency in each of the paths, in each of the routes. Now this code snippet that you see, the first part of that is a function that's calculating the time difference. And if the time difference is more than 1 second, or you can take any number, but we have just taken 1 second as a latency value. So if that value on any route is more than 1 second for a packet, then we will trigger an email. We'll basically raise a ticket with a tool called Freshdesk, which is a ticketing tool used by many organizations. So that ticketing tool will have a message that will contain the route that had latency, and the monitoring team will take the necessary action to fix that, because we didn't, as of now, we didn't plan on how to fix the issue. So this is a small video that, so we tried to just capture what we did. So one part of the screen is the part that's sniffing the packet back at dev1, and the other part is actually running the entire script, which has pro packets. So you can see the message there, highlighted part. It says delay in this route is higher than the threshold, so we are creating a new ticket based on the latency or the threshold value. So the ticket looks something like this. It will have the content. So the ticket is automatically created with the content something like, there is a high latency on R1, R2, R4, R6 route. Please take necessary action. And this is now coming to the XRBGP part. We didn't know much about XRBGP, so we tried to use the file that was given to us, the JSON file, to parse some of the information, such as the neighbor ID, neighbor address, interface ID, and print it using pretty table in the UI. So for our project, this is the future scope. We would want to scale this to a higher number of devices. As of now, we did a very small test with just a few number of devices, but in future, we would like to see whether this works actually in a production network with a large number of devices. And also, we would like to add more features and more metrics apart from the latency that we tried to capture. And since we just did monitoring at the moment, we would also like to incorporate some traffic engineering where we can take some action based on the fault or based on the latency or some issue that we find. All right, so the takeaway from the entire day was we got to use KP. This was new for us, just like XRBGP and BGP-LS and NetworkX. But we did spend a lot of time using KP, just like most of you. So that was a good learning for us, and we would like to use KP and that tool in any other automation that we would do in future. And apart from that, some some things that we learned were like planning in a short amount of time. How can you plan a hack like this? We did some teamwork. We assigned different roles to each member in the team so that we could make the most of the short time. And some other things like hacking and time management. These are team members. Thank you.
Hello. Are we good? Hi, we're Team 4, or Team 0, all at the same time. We had fun trying to figure out how to do a PowerPoint onto the screen, and before that, we had fun doing the hackathon. So we're going to go into the first part of it. This is the Icmp.
All right. Hey everyone, my name is Mark. So we kind of did the same thing I think a lot of people did. We divided and conquered. So myself and David took the Icmp and NetworkX and determining the best paths. So myself or David, I don't think we had any experience with Icmp before. So we spent a lot of time trying to figure out how the data came back when it was stored, trying to figure out how we could normalize it, put it into JSON. So spent a lot of time there. Finally, we got the data normalized. We have it now to the point where all the structures in place where we can populate the NetworkX graphs. What you see up here is manually populated, but all the nodes are being populated with code. And the first block of addresses are also being populated with code. Again, data that's being received by Icmp. I would say next steps are to also, same thing, we manually added the weights in here. They were all communicated as 10, so it'd be nice if we had some different weights. We noticed that those values weren't being introduced into Icmp for some reason, so we were just able to manually see that the weights were 10. I know that we can get the weights pretty easily, but yeah, next steps are the framework is all there to make all of this completely done with code versus going in and hand jamming it, which I think most teams did, at least for the NetworkX piece. And yeah, I'm going to hand it off for the monitoring piece, Scappy.
All right, then we did the Scappy piece, which we divided into two probes, and the probe code and the receive code. The probe code was just sending the timestamp in the payload and the segment it was going over based upon some manually entered data. And then this is the receive code, so that's cool. So this, off that payload, what would happen would be in Scappy, it would throw that packet to that function called calculate RTT, and it would print it off into the file, and it'd be good. This is the probe that we're doing, but most of it was just manually entered. This is the output. We did it by segments instead of hops, just like segment 1 would be R2, R3, R4, R6. Test that segment, here's your RTT, and then just send the probe packets as it will. So that was it. Thanks.
I'm just going to show the code piece. Yeah, say one. We still have some time. Oh, shit, a minute. Fantastic. So yeah, this is just the piece of code running, but what I meant by framework is we come up in here and let's look at the code really quickly. We were able to get use the microphone, please? Yeah, sorry. It's kind of hard to drive and use the microphone. So we were able to get the structure down, get everything put into the correct dictionaries, and start getting the data in. As you can see, all the nodes are being added in. But the edges, of course, like again, I think what most people did was putting these in manually and then running it through the canned NetworkX methods. Router info, again, all dynamically brought in. So I figured another team showed code, I'd show some code that we worked on too. So 1 minute. And that's it. Thanks.
All right. I think we have enough votes in. So we are going to call it a tie between NetBuffs and PyCon. So a round of applause really to everybody who hacked well and learned a lot and hopefully made new friends today. Let's do the raffle. And so the stuff that we're raffling off this time, so everybody pull out your cards. We have a total of 8 things that we're giving away. 4 of the Circuit Playground Express from Adafruit. And we also have CanaKit's Raspberry Pi B+, so you can build your own console servers.
Okay, I will pull a ticket. And if you have it, come on up. 59160077. Are you here? You must be present to win, that's right. Okay. Oh, you are here. Okay, good. Okay. All right. Choose Pi or an Ada thing. Okay. What?
You have to hand it out.
Oh, I have to hand it to you.
Yeah. Thank you.
Okay. All right. Okay, we're going to alternate now. This one is for the Circuit Playground Express, which looks cool. Okay, I chose a number at random. 59160079. There you go. Enjoy. All right. Oh. Here. Handing it to you. There we go. Okay. Random choice here. Okay.
So you hand them out and you don't let go until the photo's taken.
Right, exactly. I have to be showing. Okay, 5916106. 6106. Going once. Going twice. You're there. Good. Okay. All right. You get a Raspberry Pi. Okay. All right. For another one of these. Okay. What am I doing? Okay. Oh, there's one here. Okay, that's why I lost count. Okay. Five 6090. 6090. Anybody? Yeah, okay. Here you go. He's going to take your picture.
So,
You keep it. It's yours.
thank you.
You're welcome. Okay. Raspberry Pi again. All right. 5916073. Looks right. Okay, here you go. Congratulations.
All right, thank you.
Okay. For this one, 5916061. There you go. And he's going to take your picture. There we go. Okay. All right. The last Raspberry Pi goes to, you guys have gotten a lot faster at checking your tickets, by the way. I appreciate that. 5916092. There you go. He's going to take a picture. Oh, okay. All right, and today's last prize goes to 5916058. Here, maybe we can build a console server out of this.
Maybe. Thank you.
Okay.
Thank you.
All right, thanks.
I just posted a link to the survey for the hackathon. If you could please complete that and give us your feedback on your experience today, that'd be appreciated. I posted it in the Slack channel. It's also on the same page where the surveys will be for the rest of the NANOG conference. So if you don't fill it out now, please fill it out this week. Thanks.
And so thanks again for everybody who participated in here. I hope everybody had a good experience. There's a reception right outside, so please, everybody, go to it, drink and eat and be merry. Be sure to talk to other people that you haven't yet talked to today, especially thank our sponsors from Oracle and Tesuto. For the teams that won, please come and see me and Syed from Oracle to figure out how we're going to do the presentations during the plenary session. That's going to be on Tuesday afternoon. Everybody, please save any work that you care about that happened on these development machines. We're going to be destroying all the virtual infrastructure later tonight. I don't think the PyCon team is going to be worried about this since they didn't use the virtual infrastructure, but for Team Buffs, we're going to leave your stuff around so that you can get a presentation together for Tuesday. If there's any other questions, please come and talk to me or anybody else from the sponsors or the hackathon team. And again, thank you very much and see you outside.